Hash function. In this video, we are going to see about basics of hash function. Function that maps a variable length data block or message into a fixed length value called a hash code. The function is designed in such a way that when protected, it provides an authenticator to the data or message, also referred to as a message digest. A hash value is generated by a function h of the form h is equal to h of m, where m is a variable length message and h of m is a fixed length hash value. The hash value is appended to the message at the source at a time when the message is assumed or known to be correct. Cryptographic hash function. In this video, we are going to see about cryptographic hash function. A cryptographic hash function is a kind of algorithm that can be run on a piece of data, often an individual file, producing a value called a checksum. Two files can be assured to be identical only if the checksums generated from each file using the same cryptographic hash function are identical. A hash function is a more generic term that is usually used to encompass cryptographic hash function along with other sorts of algorithms like cyclic redundancy checks. Cryptographic hash functions are implemented in information security to evaluate the integrity of data, authentication control, and other security mechanisms. Cryptographic hash functions work by generating the checksum value of a data object. If the data is intentionally or unintentionally modified, the checksum value is changed. Thus, a data object's integrity may be evaluated by comparing and verifying previous and current checksums. Cryptographic hash functions must exhibit pre-image resistance, second pre-image resistance, and collision resistance properties to ensure resilience against any cryptoclastic attack. Common examples of cryptographic hash functions are MD5 and SHA-1. Cryptographic hash functions are originally devised for one specific purpose. Their use has grown to satisfy a wide variety of goals including encryption, authentication protocols, password management. Cryptographic hash functions are implemented in a variety of protocols and settings. Examples of cryptographic hash function. In this video, we are going to learn about examples of cryptographic hash function. Some of the examples of hashes are verifying file integrity, hashing passwords, digital signature. Verifying file integrity. The most obvious use is verifying file integrity. If the user downloads a large piece of software from a website, then he needs to verify its integrity. One way is to download the file again and compare the bits. If the bits are the same, then it has no issues. If they are different, then they have some issues. Hashing passwords. It is very common but less obvious. It is the process of hashing the access passwords and reiterate that hashing is not encryption. It is a bad idea for computer systems to store passwords in clear text because if the attacker somehow gets the location where they are stored, then he gets all the passwords. A more secure way is to store a hash of the password rather than the password itself. Digital signature. This is quite a bit more complicated. Signing a document electronically is not the digital equivalent of placing an autograph on paper. Thus, in this concept, one signs a document with encrypted value of the hash value of the document. Then at some later date, we can prove that the user has signed the document by decrypting the signature with the user's public key, which yields the hash, and showing that the document's hash matches the signed one. Birthday attack. In this video, we are going to learn about birthday attack. Birthday attacks are a class of brute force techniques used in an attempt to solve a class of cryptographic hash function problems. These methods take advantage of functions which, when supplied with a random input, return one of k equally likely values. By repeatedly evaluating the function for different inputs, the same output is expected to be obtained after about 1.2, that is square root k evaluations. The birthday attack makes use of what's known as birthday paradox to try to attack cryptographic hash functions. The birthday paradox can be stated as follows. What is the minimum value of k such that the probability is greater than 0.5 that at least 2 people in a group of k people have the same birthday? It turns out that the answer is 23, which is quite a surprising result. In other words, if there are 23 people in a room, the probability that 2 of them have the same birthday is approximately 0.5. If there is 100 people, that is k is equal to 100, then the probability is 0.9999997. That is, you're almost guaranteed that there will be a duplicate. A graph of the probabilities against the value of k is shown in figure. Although this is the case for birthdays, we can generalize it for n equally likely values. In the case of birthdays, n is equal to 365. So the problem can be stated like this. Given a random variable, that is an integer with uniform distribution between 1 and n, and a selection of k instances, that is k is less than or equal to n of the random variable, what is the probability p of n comma k that there is at least one duplicate? It turns out that this value is p of n comma k is equal to 1 minus n factorial divided by n minus k factorial into n power k is equal to 1 minus of 1 minus 1 by n into 1 minus 2 by n into and so on up to 1 minus k minus 1 divided by n. Take it that the following inequality holds. 1 minus x is less than or equal to e power minus x. Then we have p of n comma k is greater than 1 minus e power minus 1 by n into e power minus 2 by n and so on up to e power minus k minus 1 divided by n greater than 1 minus e power minus 1 by n plus 2 by n plus and so on up to k minus 1 by n greater than 1 minus e power minus of k into k minus 1 the whole divided by 2n. We would like to know when p of n comma k is greater than 0.5, so we set the right hand side of the equation 3 to 0.5. 0.5 is equal to 1 minus e power minus k into k minus 1 divided by 2n. ln of 2 is equal to k into k minus 1 divided by 2n. For large values of k, we can replace k into k minus 1 by k square, giving k is equal to square root of 2 into ln 2 into n is equal to 1.18 square root of n, which is equivalent to square root of n, which can be seen to be almost equal to 23 for n is equal to 365. In terms of hash code, which takes a variable length message m and produces a fixed length message digest. Assuming the length of the digest is m, then there will be 2 power m possible message digest. The length of m will generally be greater than m. This implies that more than one message can be mapped to the same digest. The idea is to make computationally infeasible to find two messages that map to the same digest. If k random messages apply to the hash code, then what must be the value of k, which makes the probability of 0.5 that at least one duplicate? Using equation 5, we have k is equal to square root of 2 power m, which is equal to 2 power m by 2. Using this idea, we can discuss the birthday attack as follows. The source A is prepared to sign a message by appending the appropriate m-bit hash code and encrypting that hash code with A's private key. The opponent generates 2 power n by 2 variations on the message, all of which convey essentially the same meaning. The opponent prepares an equal number of messages, all of which are variations of the fraudulent message, to be substituted for the real one. The two sets of messages are compared to find a pair of messages that produce the same hash code. The probability of success is greater than 0.5. If no match is found, additional valid and fraudulent messages are generated until a match is made. The opponent offers a valid variation to A for signature. This signature can then be attached to the fraudulent variation for transmission to the intended recipient. Because the two variations have the same hash code, they will produce the same signature. The opponent is assured of success even though the encryption key is not known. If we use a 64-bit hash code, then the level of effort required is only on the order of 2 power m by 2 is equal to 2 power 64 by 2 is equal to 2 power 32, which is clearly not sufficient to withstand today's computational systems. The generation of many variations that convey the same meaning is not that difficult as figure below shows. Collision-resistant attacks. In this video, we are going to see about collision-resistant attacks. In collision-resistant attack, the attacker finds two messages or data blocks x and y that yields the same hash function h of x is equal to h of y. This turns out to require considerably less effort than a pre-image or second pre-image attack. The effort required is explained by the mathematical result referred to as the birthday paradox. In essence, if we choose random variables from a uniform distribution in the range 0 through n-1, then probability that a repeated element is encountered exceeds 0.5 after square root of n choices have been made. Thus, for an m-bit hash value, if we pick data blocks at random, we can expect to find two data blocks with the same hash value within square root of 2 power m is equal to 2 power m by 2 attempts. The strategy to use the birthday paradox in a collision-resistant attack is as follows. The source A is prepared to sign a legitimate message X by appending the approximate m-bit hash code and encrypting that hash code with A's private key. The opponent generates 2 power m by 2 variations, x dash of all which convey essentially the same meaning, and stores the messages and their hash values. The attacker prepares a fraudulent message for which A's signature is desired. The attacker generates minor variations of y dash, all of which convey essentially the same meaning. For each y dash, the opponent computes h of y dash, checks for matches with any of the h of x dash values, and continues until a match is found. That is, the process continues until a y dash is generated with a hash value equal to the hash value of one of the x dash values. The opponent offers the valid variation to A for signature. This signature can then be attached to the fraudulent variation for transmission to the intended recipient. Because the two variations have the same hash code, they will produce the same signature. The opponent is assured of success even though the encryption key is not known. Thus, if a 64-bit hash code is used, the level of effort required is only on the order of 2 power 32. The generation of many variations that convey the same meaning is not difficult. To summarize, for a hash code of length, the level of effort required, as we have seen, is proportional to pre-image resistant 2 power m, second pre-image resistant 2 power m, collision resistant 2 power m by 2. If collision resistance is required, then the value 2 power m by 2 determines the strength of the hash code against brute force attacks. The 128-bit code may be viewed as inadequate. Thus, 160 bits hash length is introduced. This requires 4000 years to find a collision, but now in today's technology, as the time is much shorter, the 160 bits is now suspect. Multi-collisions attack. In this video, we are going to see about multi-collision attacks. A multi-collision for a function is a set of inputs whose outputs are all identical. A multi-collision is a generalized notion of collision on a function. For an ideal secure hash function with n-bit output, the complexity to find a k that is multi-collision needs about order of 2 power n of k minus 1 the whole divided by k computations. Here, a k collision consists of k different messages which are compressed to the same hash value. Using the flaw of the iterated structure of the hash functions, Jokes proposed a method to construct 2 power t collisions based on the pairwise collisions. Jokes showed that for any iterated hash function, it is relatively easy to find a 2 power t collision, and it only costs t times as much as that of finding an ordinary pairwise collision. Based on the result, Jokes proved that the concatenation of several hash functions does not increase their security. Motivated by Shammis and Jokes' method, we provide a new attack to build the multi-collisions and multi-near collisions towards hash functions directly instead of the combined multi-collisions from the pairwise collisions. The multi-near collisions is a generalization for the pairwise near collisions presented by Beham and Chen 1. The difference between two types of multi-collision is shown in figure. Second pre-image attack. Second pre-image attack on Merkle-Damgard hash. We now describe a new technique to find second pre-images on a Merkle-Damgard hash. It relies heavily on the diamond structure introduced by Kelsey and Kono. A diamond of size L is a multi-collision that has the shape of the complete converging binary tree of depth L with 2 power L leaves. Its nodes are labeled by chaining values over n bits, and its edges are labeled by message blocks over m bits, which map between the chaining values at the two ends of the edge by the compression function. Thus, from any of the 2 power L leaves, there is a path labeled by L message blocks that leads to the same target value ht, labeling the root of the tree. Let M be a target message of length 2k blocks. The main idea of our attack is that connecting a message to a collision tree can be done in less than 2 power n work. Moreover, connecting the root of the tree to one of the 2 power k chaining values encountered during the computation of h power f of m takes only 2 power n minus k compression function calls. The attack works in 4 steps as described below. Pre-processing step: compute a collision tree of depth L with an arbitrary target value ht. Note that this has to be done only once and can be reused when computing second pre-images of multiple messages. Connect the target ht to some chaining value in the message m. This can be done by generating random message blocks b until f of ht, b is equal to h I0 for some I0, L plus 1 is less than or equal to I0 less than modulus of m. Let b0 be a message block satisfying this condition. Generate an arbitrary prefix p of size I0 minus L minus 1 blocks whose hash is one of the chaining values labeling a leaf. Let h is equal to h power f of p be this value, and let t be the chain of L blocks traversing the tree from h to ht. Form a message. M dash is equal to p exactly divides t, exactly divides b0, exactly divides x I0 plus 1, and so on up to x2 into k. Messages m dash and m are of equal length and hashed to the same value before strengthening, so they produce the same hash value despite the Merkle-Damgard strengthening. Herding attack. The herding attack is a chosen target pre-image attack on Merkle-Damgard constructions. In the attack, an adversary commits to a public digest value ht. After the commitment phase, the adversary is challenged with a prefix p which she has no control over, and she is to produce a suffix s for which hd is equal to h par t of p by s. The main idea behind this attack is to store 2 power L possible chaining values, d is equal to hi, from which the adversary knows how to reach hd. To construct this data structure, which is in fact a tree, the adversary picks about 2 power n by 2 minus L by 2 plus 1 by 2 single block messages mj and evaluates f of hi, mj for all I and j. Due to the large number of values, it is expected that collisions occur, and it is expected that the adversary knows for all 2 power L values of hi a corresponding message block ma of I such that the set f of hi, ma of I contains only 2 power L minus 1 distinct values. The process is then repeated L minus 1 more times until a final digest value is found. These values and the corresponding message blocks are called a diamond structure as presented in given figure. In the online phase of the attack, the adversary tries at random message blocks M group until F group of P exactly divides M group belongs to D. Once such a value is found, it is possible to follow the path connecting this value to the committed hash, which is at the root of the diamond, and produce the record suffix S. The total time complexity of the attack is about 2 power n by 2 minus L by 2 plus 2 offline compression function evaluations and 2 power n minus L online compression function evaluations. MD5 Message Digest Algorithm. In this video, we are going to learn about Message Digest Algorithm. The MD5 Message Digest algorithm was developed by Ron Rivest at MIT. MD5 was the most widely used secure hash algorithm. The algorithm takes as input a message of arbitrary length and produces as output a 128-bit message digest. The input is processed in 512-bit blocks. The processing consists of the following steps. Step 1. Append padding bits. The message is padded so that its length in bits is congruent to 448 modulo 512. Length is equal to 448 mod 512. The length of the padded message is 64 bits, less than an integer multiple of 512 bits. Padding is always added even if the message is already of the desired length. Step 2. Append length. A 64-bit representation of the length in bits of the original message before the padding is appended to the result of step 1, least significant byte first. If the original length is greater than 2 power 64, then only the low-order 64 bits of the length are used. Thus, the field contains the length of the original message modulo 2 power 64. The outcome of the first two steps will result a message that is an integer multiple of 512 bits in length. Step 3. Initialize MD buffer. A 128-bit buffer is used to hold intermediate and final results of the hash function. The buffer can be represented as 4 32-bit registers A, B, C, D. These registers are initialized to the 32-bit integers hexadecimal values. A is equal to 67452301, B is equal to EFCDAB89, C is equal to 98BADCFE, D is equal to 10325476. These values are stored in little endian format, which is the least significant byte of a word in the low address byte position. As 32-bit strings, the initialization values, that is hexadecimal, appear as word A 01234567, word B 89ABCDEF, word C FEDCBA98, word D 76543210. Step 4. Process message in 512-bit, that is 16-word blocks. The heart of the algorithm is a compression function that consists of 4 rounds of processing. This module is labeled HMD5. The 4 rounds have a similar structure, but each uses a different primitive logical function referred to as F, G, H, and I in the specification. Each round takes as input the current 512-bit block being processed, that is YQ, and the 128-bit buffer value A, B, C, D, and updates the contents of the buffer. Each round also makes use of 1/4 of a 64-element table T64 constructed from the sine function. The ith element of T, denoted T of I, has the value equal to the integer part of 2 power 32 into ABS sin I, where I is in radians. Because ABS sin I is a number between 0 and 1, each element of T is an integer that can be represented in 32 bits. The table lists the values of T. The output of the 4th round is added to the input to the first round, CVQ, to produce CVQ plus 1. The addition is done independently for each of the 4 words in the buffer, with each of the corresponding words in CVQ using addition modulo 2 power 32. Step 5. Output. After all L512-bit blocks have been processed, the output from the Lth stage is 128-bit message digest. We can summarize the behavior of MD5 as follows. CV0 is equal to IV. CVQ plus 1 is equal to sum 32 of CVQ RF1 of YQ RFH of YQ RFG of YQ RFF YQ CVQ. MD is equal to CVL, where IV is equal to initial value of the ABCD buffer defined in step 3. YQ is equal to the qth 512-bit block of the message. L is equal to the number of blocks in the message, including padding and length fields. CVQ is equal to chaining variable processed with the qth block of the message. RF is equal to round function using primitive logical function X. MD is equal to final message digest value. Sum 32 is equal to addition modulo 2 power performed separately on each word of the pair of inputs. MD5 compression function. In this video, we are going to see about MD5 compression function. Let us look in more detail at the logic in each of the 4 rounds of the processing of one 512-bit block. Each round consists of a sequence of 16 steps operating on the buffer A, B, C, D. Each step is in the form A is equivalent to B plus A plus G of B, C, D plus X of K plus T of I to the left by S, where A, B, C, D is the 4 words of the buffer in a specified order that varies across steps. G is equal to one of the primitive functions F, G, H, I. To the left of S means circular left shift rotation of the 32-bit argument by S bits. Xk is equal to M of Qx 16 plus K is equal to the kth 32-bit word in the qth 512-bit block of the message. Ti is equal to the ith 32-bit word in matrix T. Plus is equal to addition modulo 2 power 32. The order in which the 4 words A, B, C, D are used produces a word-level circular right shift of one word for each step. One of the 4 primitive logical functions is used for each of the 4 rounds of the algorithm. Each primitive function takes 3 32-bit words as input and produces a 32-bit word output. Each function performs a set of bitwise logical operations, that is, the nth bit of the output is a function of the nth bit of the 3 inputs. Secure hash algorithm SHA. In this animation, we are going to learn about secure hash algorithm. From the brute force attack point of view, MD5 is now vulnerable to birthday attacks that require on the order of effort of 2 power 64. As a result, There is a need to replace the popular MD5 with a hash function that has a longer hash code and is more resistant to known methods of cryptanalysis. Hence, it gave emergence to SHA-1 and RIPEMD 160. Its secure hash algorithm SHA was developed by the National Institute of Standards and Technology (NIST) and published as the Federal Information Processing Standard FIPS PUB 180 in 1993. A revised version was issued as FIPS PUB 181 in 1995 and is generally referred to as SHA-1. SHA-1 logic. The algorithm takes as input a message with a maximum length of less than 2 power 128 bits and produces as output a 160-bit message digest. The input is processed in 512-bit blocks. The overall processing of a message follows the structure shown for MD5 in figure, with a block length of 512 bits and a hash length and chaining variable length of 160 bits. The processing consists of the following steps. Step 1. Append padding bits. The message is padded so that its length is congruent to 448 modulo 512. Length is equal to 448 modulo 512. Padding is always added even if the message is already of the desired length. Thus, the number of padding bits is in the range of 1 to 512. The padding consists of a single I bit followed by the necessary number of O bits. Step 2. Append length. A block of 64 bits is appended to the message. This block is treated as an unsigned 64-bit integer, most significant byte first, and contains the length of the original message before the padding. Step 3. Initialize MD buffer. A 160-bit buffer is used to hold intermediate and final results of the hash function. The buffer can be represented as 5 32-bit registers A, B, C, D, E. These registers are initialized to the following 32-bit integers, hexadecimal values. A is equal to 67452301. B is equal to EFCDAB89. C is equal to 98BADCFE. D is equal to 10325476. E is equal to C3D2EIFO. Note that the four values are the same as those used in MD5. However, in the case of SHA-1, these values are stored in big endian format, which is the most significant byte of a word in a low address byte position. As 32-bit strings, the initialization values in hexadecimal appear as follows. Word A 67452301. Word B EFCDAB89. Word C 98BADCFE. Word D 10325476. Word E C3D2EIFO. Step 4. Process message in 512-bit 16-word blocks. The heart of the algorithm is a module that consists of 4 rounds of processing of 20 steps each. The 4 rounds have a similar structure, but each uses a different primitive logical function which we refer to as F1, F2, F3, and F4. Each round takes as input the current 512-bit block being processed YQ and the 160-bit buffer value A, B, C, D, E and updates the contents of the buffer. In fact, only 4 distinct constants are used. The values in hexadecimal and decimal are as follows. The output of the fourth round, 80th step, is added to the input to the first round CVQ to produce CVQ plus 1. The addition is done independently for each of the 5 words in the buffer with each of the corresponding words in CVQ using addition modulo 2 power 32. After all L 512-bit blocks have been processed, the output from the L stage is the 160-bit message digest. We can summarize the behavior of SHA1 as follows. CV0 is equal to IV. CVQ plus 1 is equal to sum 32 of CVQ A, B, C, D, E. MD is equal to CVL, where IV is equal to initial value of the A, B, C, D, E buffer defined in step 3. A, B, C, D, E, Q is equal to the output of the last round of processing of the Qth message block. L is equal to the number of blocks in the message including padding and length fields. Sum 32 is equal to addition modulo 2 power 32 performed separately on each word of the pair of input. MD is equal to final message digest value. SHA1 compression function. In this video, we are going to learn about SHA1 compression function. The more detail of the logic in each of the 80 rounds of the processing of 512-bit block A, B, C, D, E is equivalent to E plus F of T, B, C, D plus S power 5 of A plus WT plus KT, A, S power 30 of B, C, D, where A, B, C, D, E are the 5 words of the buffer. T is the step number, where 0 less than or equal to T less than or equal to 79. F of T, B, C, D is equal to primitive logical function for step T. S power K is equal to circular left shift rotation of the 32-bit argument by K bits. WT is equal to a 32-bit word derived from the current 512-bit input block. KT is equal to an additive constant. 4 distinct values are used as defined previously. Plus is addition modulo 2 power 32. Each primitive function takes 3 32-bit words as input and produces a 32-bit word output. Each function performs a set of bitwise logical operators, that is, the nth bit of the 3 inputs. The logical operators AND, OR, NOT, XOR are represented by the symbols as only 3 functions are used. For 0 less than or equal to T less than or equal to 19, the function is the conditional function if B then C else D. For 20 less than or equal to T less than or equal to 39 and 60 less than or equal to T less than or equal to 79, the function produces a parity bit. For 40 less than or equal to T less than or equal to 59, the function is true if 2 or 3 of the arguments are true. It remains to indicate how the 32-bit word values W are derived from the 512-bit message. The first 16 values of W are taken directly from the 16 words of the current block. The remaining values are defined as follows. WT is equal to S power 1 of WT minus 16 XOR with WT minus 14 XOR with WT minus 8 XOR with WT minus 3. Thus, in the first 16 steps of processing, the value of W is equal to the corresponding word in the message block. For the remaining 64 steps, the value of W consists of the circular left shift by 1 bit of the XOR of 4 of the preceding values of WT. This is a notable difference from MD5 and RIPE MD160, both of which use one of the 16 words of a message block directly as input to each step function. Only the order of the words is permuted from round to round. SHA1 expands the 16 block words to 80 words for use in the compression function. This introduces a great deal of redundancy and interdependence to the message blocks that are compressed, which complicates the task of finding a different message block that maps to the same compression function output. SHA256. In this video, we are going to see about SHA-256. SHA-256 operates in the manner of MD4, MD5 and SHA-1. The message to be hashed is first padded with its length in such a way that the result is a multiple of 512 bits long and then parsed into 512 bit messages block m power 1, m power 2 and so on up to m power n. The message blocks are processed one at a time, beginning with a fixed initial hash value h power 0, sequentially compute h power I is equal to h power I minus 1 plus c m power I into h power I minus 1, where c is the SHA-256 compression function and plus means worldwise mod 2 power 32 addition, h power n is the hash of m. Description of SHA-256. The SHA-256 compression function operates on a 512-bit message block and a 256-bit intermediate hash value. It is essentially a 256-bit block cipher algorithm which encrypts the intermediate hash value using the message block as key. Hence, there are two main components to describe: the SHA-256 compression function, the SHA-256 message schedule. We will use the following notation: bitwise XOR, bitwise AND, bitwise OR, bitwise complement, plus mod 2 power 32 addition, R power n write shift by n bits, S power n write rotation by n bits. The initial hash value h power 0 is the following sequence of 32-bit words which are obtained by taking the fractional parts of the square roots of the first 8 primes. Pre-processing. Computation of the hash of a message begins by preparing the message. Pad the message in the usual way. Suppose the length of the message m in bits is L. Append the bit 1 to the end of the message and then k0 bits, where k is the smallest non-negative solution to the equation L plus 1 plus k is equal to 448 mod 512. To this, append the 64-bit block which is equal to the number L written in binary. For example, the 8-bit ASCII message ABC has length 8 into 3 is equal to 24, so it is padded with a 1, then 448 minus 24 plus 1 is equal to 423 0 bits, and then its length to become the 512-bit padded message. The length of the padded message should now be a multiple of 512 bits. Parse the message into n 512-bit blocks, m power 1, m power 2 and so on up to m power n. The first 32 bits of message block I are denoted m0 power I. The next 32 bits are m1 power I and so on up to m15 power I. We use the big endian convention throughout, so within each 32-bit word, the leftmost bit is stored in the most significant bit position. Definitions. 6 logical functions are used in SHA-256. Each of these functions operates on 32-bit words and produces a 32-bit word as output. SHA-384. In this animation, we are going to learn about SHA-384. SHA-384 is defined in the exact same manner as SHA-512 with the following two exceptions. The initial hash value h power 0 is based on the fractional parts of the square roots of the 9th through 16th primes. h1 power 0 is equal to CBBB 9D 5D C105 9ED8. h2 power 0 is equal to 629A 292A 367C D507. h3 power 0 is equal to 9159-015A 3070 DD17. h4 power 0 is equal to 152F ECD8 F70E 5939. h5 power 0 is equal to 6733-2667 FFC0 0B31. h6 power 0 is equal to 8EB4 4A87 68581511. H7 power 0 is equal to DB0C 2E0D 64F9 8FA7. H8 power 0 is equal to 47BF 481D BEFA 4FA4. The final 384-bit hash is obtained by truncating the SHA 512-based hash output to its leftmost 384 bits. Hence, the hash of ABC is CB00753F45A3 5E8B B5A0 3D699AC6 5007 272C 32AB 0EDE D163 1A8B 605A 43FF 5BED 8086 072B A1E7 CC23 58BA ECA1 34CA 25A7 and hash of A B C D E F G H B C D E F G H I C D E F G H I J D E F G H I J K E F G H I J K L F G H I J K L M G H I J K L M N H I J K L M N O I J K L M N O P J K L M N O P Q K L M N O P Q R LMNOPQRS, MNOPQRST, NOPQRSTU. With no break after the first N is 09330C33 F71147E8 3D19 2FC7 82CD 1B47 5311 1B17 3B 3B05D2 2FA08086 E3B0 F712 FCC7 C71A 557E 2DB9 66C3 E9FA 9174 6039. SHA 512. In this video, we are going to learn about SHA 512. SHA 512 is a variant of SHA 256 which operates on 8 64-bit words padded with its length in such a way that the result is a multiple of 1024 bits long. Parsed into 1024-bit message blocks M-power1, M-power2 and so on up to M-power n. The message blocks are processed one at a time, beginning with a fixed initial hash value h-0, sequentially compute h-i is equal to h-i minus 1 plus c m-i of h-i minus 1, where c is the SHA 512 compression function and plus means word-wise mod 2^64 addition. h-n is the hash of m. Description of SHA 512. The SHA 512 compression function operates on a 1024-bit message block and a 512-bit intermediate hash value. It is essentially a 512-bit block cipher algorithm which encrypts the intermediate hash value using the message block as key. Hence, there are two main components to describe the SHA 512 compression function and the SHA 512 message schedule. We will use the following notation: bitwise XOR, bitwise AND, bitwise OR, bitwise complement, plus mod 2^64 addition, R(n) write shift by n bits, S(n) write rotation by n bits. For SHA 512, all of these operators act on 64-bit words. The initial hash value h(0) is the following sequence of 64-bit words which are obtained by taking the fractional parts of the square roots of the first 8 primes. Pre-processing. Computation of the hash of a message begins by preparing the message. Pad the message in the usual ways. Suppose the length of the message m in bits is L. Append the bit 1 to the end of the message and then k0 bits, where k is the smallest non-negative solution to the equation L plus 1 plus k, which is congruent to 896 mod 1024. To this, append the 128-bit block which is equal to the number L written in binary. For example, the 8-bit ASCII message ABC has length 8 into 3 is equal to 24, so it is padded with a 1, then 896 minus 24 plus 1 is equal to 8710 bits, and then its length to become the 1024-bit padded message. The length of the padded message should now be a multiple of 1024 bits. Parse the message into n 1024-bit blocks, m power 1, m power 2, and so on up to m power n. The first 64 bits of message block I are denoted m0 power I, the next 64 bits are m1 power I, and so on up to m15 power I. We use the big endian conversion throughout, so within each 64-bit word, the leftmost bit is stored in the most significant bit position. Definitions. 6 logical functions are used in SHA 512. Each of these functions operates on 64-bit words and produces a 64-bit word as output. RIPEMD160. In this video, we are going to learn about RIPEMD160. The RIPEMD160 message digest algorithm DOBB96B BOSS 971 was developed under the European RACE Integrity Primitives Evaluation (RIPE) project by a group of researchers that launched partially successful attacks on MD4 and MD5. The algorithm takes as input a message of arbitrary length and produces as output a 160-bit message digest. The input is processed in 512-bit blocks. Step 1. Append padding bits. The message is padded so that its length is congruent to 448 modulo 512. Its length is equal to 448 mod 512. Padding is always added even if the message is already of the desired length. Thus, the number of padding bits is in the range of 1 to 512. The padding consists of a single 1 bit followed by the necessary number of 0 bits. Step 2. Append length. A block of 64 bits is appended to the message. This block is treated as an unsigned 64-bit integer, least significant byte first, and contains the length of the original message before the padding. Step 3. Initialize MD buffer. A 160-bit buffer is used to hold intermediate and final results of the hash function. The buffer can be represented as 5 32-bit registers A, B, C, D, E. These are the same values used in SHA-1, and the first 4 are the same values used in MD5 as in MD5. These values are stored in little endian format. Step 4. Process message in 512-bit, that is 16 word blocks. The heart of the algorithm is a module that consists of 10 rounds of processing of 16 steps each. The 10 rounds are arranged as 2 parallel lines of 5 rounds. The 10 rounds have a similar structure, but each uses a different primitive logical function, which we refer to as F1, F2, F3, F4, and F5. Note that the functions are used in reverse order in the right line. Each round takes as input the current 512-bit block being processed Y and the 160-bit buffer value A, B, C, D, E left line or A dash, B dash, C dash, D dash, E dash right line and updates the contents of the buffer. Each round also makes use of an additive constant. In fact, only 9 distinct constants are used, one of which is 0. The values in hexadecimal and decimal are shown in the below table. The output of the 5th round, that is 80th step, is added to the chaining variable input to the first round CVQ to produce CVQ plus 1. The addition is done independently for each of the 5 words in the buffer of each line, with each of the words in CVQ using addition modulo 2 part 32. The addition involves a rotation of the words of each of the 3 inputs in the following fashion. Step 5. Output. After all L 512-bit blocks have been processed, the output from the L stage is the 160-bit message digest. Message Authentication Codes MAC. In this video, we are going to learn about Message Authentication Codes MAC. Message Authentication Codes MAC. Message Authentication Code or MAC is obtained by applying a secret key to the message digest so that the holder of the secret key can compute the MAC from the digest and hence the message. This method thwarts a threat posed by a malicious interceptor who could modify the message and replace the digest with a digest of the modified message, for the interceptor would not have access to the secret key. There should be a secure way to share the secret key between the sender and the recipient for this to work. A MAC, also known as a cryptographic checksum, is generated by function C of the form MAC is equal to CK of M. A to B, EK of M equally divides H of M, provides confidentiality, only A and B share K, provides authentication, H of M is cryptographically protected. A gives B, M equally divides EK of H of M, provides authentication, H of M is cryptographically protected. A gives B, M equally divides EKRA of H of M, provides authentication and digital signature. H of M is cryptographically protected, only A could create EKRA of H of M. A gives B, EK of M equally divides EKRA of H of M, provides authentication and digital signature, provides confidentiality, only A and B share K. A gives B, M equally divides H of M equally divides S, provides authentication, only A and B share S. A gives B, EK of M equally divides H of M, which equally divides S, provides authentication, only A and B share S, provides confidentiality, only A and B share K. Where M is a variable length message, K is a secret key shared only by sender and receiver, and C. M is the fixed length authenticator. The MAC is appended to the message at the source at the time when the message is assumed or known to be correct. The receiver authenticates that message by recomputing the MAC. Requirements for MACs. In this video, we are going to learn about requirements for MACs. Requirements for MACs. When an entire message is encrypted for confidentiality using either symmetric or asymmetric encryption, the security of the scheme generally depends on the bit length of the key. Barring some weakness in the algorithm, the opponent must resort to a brute force attack using all possible keys. On average, such an attack will require 2 power k-1 attempts for a k-bit key. In particular, for a ciphertext-only attack, the opponent, given ciphertext C, would perform pi is equal to dki of C for all possible key values ki until a pi was produced that matched the form of acceptable plaintext. In the case of a MAC, the considerations are entirely different. In general, the MAC function is a many-to-one function. The domain of the function consists of messages of some arbitrary length, whereas the range consists of all possible MACs and all possible keys. If an n-bit MAC is used, then there are 2 per possible MACs, whereas there are n possible messages with n much greater than 2 per. Furthermore, with a k-bit key, there are 2 per k possible keys. Using brute force methods, if confidentiality is not employed, the opponent has access to plaintext messages and their associated MACs. Suppose k is greater than n, that is, suppose that the key size is greater than the MAC size. Then, given a known M and MAC, with MAC is equal to CK1 of M1, the cryptanalyst can perform MAC I is equal to CKI of M1 for all possible key values Ki. At least one key is guaranteed to produce a match of MAC1 is equal to MAC I. Note that a total of 2 power k max will be produced, but there are only 2 power n less than 2 power k different MAC values. Thus, a number of keys will produce the correct MAC, and the opponent has no way of knowing which the correct key is. On average, a total of 2 power k by 2 power n is equal to 2 power k minus n keys will produce a match. Thus, the opponent must iterate the attack. Round 1. Given M1, MAC is equal to CK of M1. Compute MAC I is equal to CKI of M1 for all 2 power k keys. Number of matches, which is equivalent to 2 power k minus n. Round 2. Given M2, MAC is equal to CK of M2. Compute MAC I is equal to CKI of M2 for the remaining 2 power k minus n keys. Number of matches, which is equivalent to 2 power k minus 2 into n, and so on. On average, alpha rounds will be needed if k is equal to alpha into n. If the key length is less than or equal to the MAC length, then it is likely that a first round will produce a single match. It is possible that more than one key will produce such a match, in which case the opponent would need to perform the same test on a new message MAC pair. Thus, a brute force attempt to discover the authentication key is no less effort and maybe more effort than that required to discover a decryption key of the same length. However, other attacks that do not require the discovery of the key are possible. Consider the following MAC algorithm. Let M is equal to x1, x2, and so on up to xm be a message that is treated as a concatenation of 64-bit block xi. Then define A of M is equal to x1 XOR with x2 XOR with and so on XOR with xm. Thus, the key length is 56 bits and the MAC length is 64 bits. If an opponent observes M equally divides C, M, a brute force attempt to determine K will require at least 2 power 56 encryptions, but the opponent can attack the system by replacing x1 with xm-1 with any desired values y1 through ym-1 and replacing x1 with ym, where ym is calculated as follows. Ym is equal to y1 XOR with y2 and so on up to ym-1 XOR with del of m. The opponent can now concatenate the new message, which consists of y1 through ym, with the original MAC to form a message that will be accepted as authentic by the receiver. With this tactic, any message of length 64 into m-1 bits can be fraudulently inserted. Thus, in assessing the security of a MAC function, we need to consider the types of attacks that may be mounted against it. With that in mind, let us state the requirements for the function. Assume that an opponent knows the MAC function C but does not know K. Then the MAC function should have the following properties. If an opponent observes M and Ci of M, it should be computationally infeasible for the opponent to construct a message M' such that Ck of M' is equal to Ci of M. Ci of M should be uniformly distributed in the sense that for randomly chosen messages M and M', the probability that Ci of M is equal to Ci of M' is 2 power minus n, where n is the number of bits in the MAC. Let M' be equal to some known transformation on M, that is, M' is equal to f of M. For example, f may involve inverting one or more specific bits. In that case, PR of Ck of M is equal to Ck of M' is equal to 2 power minus n. The first requirement speaks to the earlier example, in which an opponent is able to construct a new message to match a given MAC, even though the opponent does not know and does not learn the key. Requirement 2 deals with the need towards a brute force attack based on chosen plaintext. That is, if we assume that the opponent does not know K but does have access to the MAC function and can present messages for MAC generation, then the opponent could try various messages until finding one that matches a given MAC. If the MAC function exhibits uniform distribution, then a brute force method would require, on average, 2 power n-1 attempts before finding a message that fits a given MAC. The final requirement dictates that the authentication algorithm should not be weaker with respect to certain parts or bits of the message than others. If this were not the case, then an opponent who had M and C I of M could attempt variations on M at the known weak spots with a likelihood of early success at producing a new message that matched the old MAC. Message authentication code based on DES. The algorithm can be defined as using the cipherblock chaining (CBC) mode of operation of DES with an initialization vector of 0. The data, for example, message, record, file or program, to be authenticated is grouped into contiguous 64-bit blocks D1, D2 and so on up to Dn. If necessary, the final block is padded on the right with zeros to form a full 64-bit block. Using the DES encryption algorithm E and a secret key K, a data authentication code DAC is calculated. Difference between hash and MAC. In this video, we are going to see the difference between hash and MAC. Cryptographic hash functions. This is a procedure that calculates a fixed size bit string hash value from a piece of data. If the data is changed while it is in storage or in transit, the hash value will also be changed. This allows a person to verify whether the data has been tampered with. Often the data will be called the message, and the hash value will be called the message digest or digest. An example would be to take basic text as data, such as the sentence "study hard for the security plus exam," and calculate a hash from the data. MAC, Message Authentication Code. This is a small piece of information used to authenticate a message. The MAC algorithm takes a message and secret key and outputs a MAC value or tag. MACs only use secret keys and rely on symmetric encryption. However, to function as intended, the MAC must be able to resist plaintext attacks even if a hacker knows the secret key. Although the hacker can create their own MACs from the key, the MAC algorithm must be strong enough to make it impossible for the hacker to calculate the MAC for other messages. MACs can be built from hash functions. These are known as keyed hash functions. Authenticated encryption. In this video, we are going to see about authenticated encryption. Authenticated encryption. Authenticated encryption (AE) is a word used to explain encryption systems that concurrently defend confidentiality and authenticity, that is, integrity of communications. Several applications and protocols need both forms of security, but until newly, the two services designed individually. 4 universal approaches to offer both confidentiality and encryption for a message M. HTE, hash then encrypt. First, calculate the cryptographic hash function over M as h is equal to h of M. Then encrypt the message plus hash function E of K, M equally divides h. MTE, MAC then encrypt. Use 2 keys. First, validate the plaintext by calculating MAC value as T is equal to MAC of K1, M. Then encrypt the message plus tag E of K2, M equally divides T. ETM, encrypt then MAC. Use two keys. First, encrypt the message to give away the ciphertext C is equal to E of K2, M. Then authenticate the ciphertext with T is equal to MAC of K1, C to yield the pair C, T. This approach is used in the IPsec protocol. E and M, encrypt and MAC. Use two keys. Encrypt the message to yield ciphertext C is equal to E of K2, M. Authenticate the plaintext with T is equal to MAC of K1, M to yield the pair C, T. These operations execute in either order. This approach is used by the SSH protocol. Counter with cipherblock chaining, message authentication code. In this video, we are going to see about counter with cipherblock chaining, message authentication code. The key algorithmic ingredient of counter with cipherblock chaining message authentication code CCM, or the Authenticated Encryption Standard AES encryption algorithm, the counter mode CTR mode of operation, and the CMAC authentication algorithm. A single key K is used for both encryption and MAC algorithms. The input to the CCM encryption process consists of three elements. Data will be both authenticated and encrypted. It is a plaintext message P of data block. Associated data A will be authenticated but not encrypted. A nonce N is allocated to the payload and the associated data. Demonstrate the operation of CCM. For authentication, the input comprises the nonce, associated data, and plaintext. The input is formatted as series of blocks B0 through BR. The first block contains the nonce plus some formatting bits that indicate the lengths of the N, A, and P elements. This is followed by 0 or more blocks that enclose A, followed by 0 or more blocks that contain P. The resulting series of blocks give out as input to the CMAC algorithm, which create a MAC value with length tlen, which is less than or equal to the block length. For encryption, a series of counters is produced that should be independent of the nonce. The authentication tag is encrypted in CTR mode using the single counter CTR0tlen. Most significant bits of the output are XORed with a tag to make an encrypted tag. The remaining counters is used for the counter mode encryption of the plaintext. The encrypted plaintext is concatenated with the encrypted tag to form the ciphertext output. SP838C defines the authentication or encryption process as follows. Apply the formatting to NAP to produce the blocks B0, B1, and so on up to BR. Set Y0 is equal to E of K, B0. For I is equal to 1 to R, do Yi is equal to E of K, Bi XOR with Yi minus 1. Set T is equal to MSB T len of YR. Apply the counter generation function to generate the counter blocks CTR0, CTR1, and so on up to CTRM, where M is equal to P len by 128. For J is equal to 0 to M, do Sj is equal to E of K, CTRJ. Set S is equal to S1 equally divides S2 and so on up to Sm. Return C is equal to P XOR with MSB P len of S equally divides T XOR with MSB T len of S0. For decryption and verification, the recipient requires the following input: the ciphertext C, the nonce N, the associated data A, the key K, and the initial counter CTR0. The steps are as follows. If C len is less than or equal to T len, then return invalid. Apply the counter generation function to generate the counter blocks CTR0, CTR1, and so on up to CTRM, where M is equal to C len by 128. For J is equal to 0 to M, do Sj is equal to E of K, CTRJ. Set S is equal to S1 equally divides S2, which equally divides and so on up to Sm. Set P is equal to MSB clen minus tlen of C XOR with MSB clen minus tlen of S. Set T is equal to LSB tlen of C XOR with MSB tlen of S0. Apply the formatting function to NAP to produce the blocks B0, B1 and so on up to BR. Set Y0 is equal to E of K, B0. For I is equal to 1 to R, do Yi is equal to E of K, Bi XOR with Yi minus 1. If T is not equal to MSB tlen of YR, then return invalid, else return P. CCM is a relatively complex algorithm. It requires 2 complete passes through the plaintext, once to generate the max value and once for encryption. In any case, 2 analyses of the algorithm conclude that CCM provides a high level of security. Galois or counter mode. In this video, we are going to see about Galois or counter mode. The Galois or counter mode GCM mode of operation is designed to be parallelizable so that it can provide high throughput with low cost and low latency. In essence, the message is encrypted in variant of CTR mode. The resulting ciphertext is multiplied with key material and message length information over GF of 2 power 128 to generate the authenticator tag. The standard also specifies a mode of operation that supplies the MAC only, known as GMAC. The GCM mode makes use of 2 functions, ghash, which is a keyed hash function, and gctr, which is essentially the CTR mode with the counters determined by a simple increment by 1 operation. Ghash h of x takes a input the hash key h and a bit string x such that len of x is equal to 128 m bits for some positive integer m and produces a 128-bit MAC value. The function may be specified as follows. Let x1, x2 and so on up to xm-1 xm denote the unique sequence of blocks such that x is equal to x1 equally divides x2, which equally divides and so on up to xm-1 equally divides xm. Let y0 be a block of 128 zeros designated as 0 power 128. For I is equal to 1 and so on up to m, let yi is equal to yi-1 XOR with xi into h, where designates multiplication in gf of 2 power 128. Return ym. The ghash h of x function can be expressed as x1 into h power m XOR with x2 into h power m-1 XOR and so on up to xm-1 into h square XOR with xm into h. This formulation has desirable performance implications. If the same hash key is to be used to authenticate multiple messages, then the values h power 2, h power 3 and so on can be pre-calculated one time for use with each message to be authenticated. Then the blocks of the data to be authenticated, x1, x2 and so on up to xm, can be processed in parallel because the computations are independent of one another. GCTR k of ICB, x takes a input a secret key k and a bit string x arbitrary length and returns a ciphertext y of bit length len of x. The function may be specified as follows. If x is the empty string, then return the empty string as y. Let n is equal to len x divided by 128. That is the smallest integer greater than or equal to len x by 128. Let x1, x2 and so on up to xn-1. Xn group denotes the unique sequence of bit strings such that x is equal to x1 equally divides x2 and so on up to xn-1 equally divides xn group. x1, x2 and so on up to xn-1 are complete 128-bit blocks. Let CB1 is equal to ICB. For I is equal to 2 to n, let CBI is equal to INC32 of CBI-1, where the INC32 of S function increments the rightmost 32 bits of S by 1 mod 2 power 32 and the remaining bits are unchanged. For I is equal to 1 to n-1, do yi is equal to xi XOR with E of k, CBI. Let yn group is equal to xn group XOR with MSB len xn group into E of k, CBN. Let x is equal to x1 equally divides x2, which equally divides and so on up to xn-1 equally divides yn group. Return y. Note that the counter values can be quickly generated and that the encryption operations can be performed in parallel. We can now define the overall authenticated encryption function. The input consists of a secret key k, an initialization vector iv, a plaintext p, and additional authenticated data a. The notation XS means the S-bit binary representation of the non-negative integer. The steps are as follows. Let h is equal to E of k, 0 power 128. Define a block J0 as if len iv is equal to 96, then let J0 is equal to iv equally divides 0 power 31 equally divides 1. If len of iv is not equal to 96, then let s is equal to 128 into len iv divided by 128 minus len iv, and let J0 is equal to g hash h of iv equally divides 0 power s plus 64 equally divides len iv 64. Let c is equal to gctr k of inc32 of J0, p. Let u is equal to 128 of len c divided by 128 minus len c, and let v is equal to 128 of len a by 128 minus len a. Define a block S as S is equal to g hash h of a equally divides 0 power v equally divides c equally divides 0 power u equally divides len a 64 equally divides len c 64. Let t is equal to MSB t of gctr k of J0, s, where t is the supported tag length. Return c, t. In step 1, the hash key is generated by encrypting a block of all zeros with a secret key. In step 2, the pre-counter block J0 is generated from the IV. In particular, when the length of the IV is 96 bits, then the padding string 0 power 31 equally divides 1 is appended to the IV to form the pre-counter block. Otherwise, the IV is padded with the IV minimum number of 0 bits, possibly none, so that the length of the resulting string is a multiple of 128 bits, the block size. This string, in turn, is appended with 64 additional 0 bits, followed by the 64-bit representation of the length of the IV, and the ghash function is applied to the resulting string to form the pre-counter block. Thus, GCM is based on the CTR mode, that is counter mode of operation, and adds a MAC that authenticates both the message and additional data that requires only authentication. The function that computes the hash uses only multiplication in a Galois field. This choice was made because the operation of multiplication is easy to perform within a Galois field and is easily implemented in hardware.